Calc 2, Friday's session is on. Okay. So, last time in class we talked about power series. And we had a power series. This was a sum from n equals 0 to infinity of c sub n and an x minus a to the n. And we call this a power series centered at A, right? And we said that this is just to give you an idea of what this looks like. Okay, so this is a power series. And we said the big theorem is 3 things can happen. Okay, there's going to be 3 things that can happen. Can you tell me what they are? What are the 3 possibilities? Yes.
It converges at A,
Converges
everywhere.
only at A. So one possibility is it only converges at A. And in this case, the radius of convergence is 0. Okay, what's the second possibility?
Converge everywhere.
Converge everywhere, and not only converge, but
Absolutely.
absolutely converge, yeah. The second possibility is that you'll have absolute convergence everywhere. And in this case, we say that the radius of convergence is infinity. And the most common case, and probably as far as what's common in the sense that the most common case for what's going to be on your exam, because this is the one I like to, you know, obviously professors like to test, is what?
The radius of convergence.
There's going to be a positive R. There exists a positive R, and you are going to get, if the absolute value of x minus a is less than R, you are going to get absolute convergence. And if the absolute value of x minus a is greater than R, you're going to get divergence. And when the absolute value of x minus a is actually equal to R, you get check your endpoints. So this big major theorem we were using is giving us the strategy that here's A, and we're looking on the real line between A plus R and A minus R, and we've got absolute convergence inside here, and we've got divergence outside here. And then right here and here, you have to check. These you have to check. Okay? So that's the story. Now because of that, if I give you an interval of convergence question or a radius of convergence question, your strategy is going to be to force the limit with, say, the ratio of the root test. Force it to be less than 1 in order to get a condition on x. Because the ratio test works when that limit that you take in the ratio test is less than 1. So you're going to force it to be less than 1 to get a condition on x. Right? This is the strategy that you're going to use. Right? So let's write that down. So your strategy is going to be force the limit as n goes to infinity of a sub n plus 1 over a sub n with the absolute value to be less than 1 to get a condition on x. In this case, in other words, you're going to force the limit as n goes to infinity of the absolute value of Cn plus 1 x minus a to the n plus 1 over C sub n x minus a to the n. You are going to force this to be less than 1. And you're going to say this is less than 1 if and only if something else about x. If and only if something else. Until you can get it down to the absolute value of x minus a is less than some r. So you're trying to reach this form. And you just basically just do, like we said, some algebra cancellations, different things, right? So that's what you're going to do. Okay, so that's just the strategy. Now let's do some of these, and then we'll do some of these problems. Then again, we'll talk about differentiating and integrating series. We'll do, in other words, we're just kind of going over Monday's class for now, until maybe about 3:45 or so, and then we'll start doing some new stuff. We'll do the Taylor series. Okay? So let's do a couple of examples. All right, let's do some more examples from the book. I'm in 10.7 on power series. Okay, the sum from n equals 0 to infinity of n x plus 3 to the n divided by 5 to the n. Okay, n x plus 3 to the n divided by 5 to the n. All right. Now this is a, well, you can do a root test, but then you have to do n to the 1 over n too, and that's an indeterminate form. Take you a little longer. So you stick with the ratio test here. So let's do the ratio test. Now where is it centered? Let's get the center first. Where's the center of this power series? Where's it centered at?
3.
Not 3, but
Negative.
-3, because it's a, x plus 3 is x minus -3. So you got to get in the x minus a form. So this is going to be at -3. And so we're going to expect that there's some radius about -3, where between -3 plus r and -3 minus r inside here, we're going to get absolute convergence. We're going to get divergence out here. And then we have to check. So you can already see that's probably where we're going in this problem, but we have to see. So I'm going to take a limit. I'm going to use the ratio test. So I'm going to take a limit as n goes to infinity, plugging in n plus 1 everywhere. To the n plus 1, and I'm going to divide by this, which is I multiply by the reciprocal. And And I'm going to put absolute values on because my nice theorem tells me that if I get convergence inside that radius of convergence, I get absolute convergence. So that's why I'm going to do that. And I'm going to force this to be less than 1. So I'm going to force it here to get a condition on x. I'm trying to see which x's make the ratio test go through. So now it's just doing the if and only ifs. So if and only if the limit as n goes to infinity, and I get some cancellations. So where are my cancellations? What did you say? There's cancellation here, so what happens? I'll get my blue marker for that, which should be in here somewhere. What happens?
Just 5.
Yeah, just 5. Okay, so out and out, just 5 there. And what else?
Z x plus 3.
Okay, this goes and now that goes.
And I think that's it.
And that's it. So now I've got a limit as n goes to infinity of the absolute value of x plus 3. And I've got an n plus 1 over a 5n. And that's less than 1. So x plus 3 is a constant as far as n is concerned on its journey towards infinity. We can take that out. Absolute value of x plus 3, limit as n goes to infinity of n plus 1 over 5n is less than 1. What is this limit? You know what that limit is. What is that limit?
1/5.
1/5. So this, now we've got the condition. We've got that all of this is true if and only if the absolute value of x plus 3 divided by 5 is less than 1, which is the same as saying the absolute value of x plus 3 is less than 5. So what's our radius of convergence?
5.
5. So we can write that down. Our R is 5. Now we're interested in our interval of convergence, our IOC, our interval of convergence. Well, we know we're looking at what? Somewhere in between -8 and 2, right? Somewhere in between -8. So we now know that between -8 and 2, centered at -3, we know we've got absolute convergence. We know we've got divergence. The only 2 points we don't know about is 2 and -8 itself. We don't know. You have to check them. What if you throw a 2 in? What do you get? You throw a 2 in for x in the series. What do you get? Series
Oh, I cancel out the. You get 5n.
cancels.
You cancel the 5.
Okay, what are you left with?
Yeah.
N. Does series n converge?
Yeah. Or no, diverge.
Diverge by what test?
Divergence.
Divergence test, yeah, n goes to infinity. As n goes to infinity, n goes to infinity, so no chance. So this endpoint is out, 2 is out. Now what about -8? If you plug in -8, what do you get?
-5 then.
Which is what? What's the cancellation? What's n minus 5 to the n divided by 5 to the n? Minus 1 to the n times n. So alternating sign n.
Yeah.
What does that series do? You put an alternating sign on n and take it as a series. Converge, really?
Oh, diverge.
It diverges
Fail the
because
decreasing test.
it fails the,
Decreasing test.
No, it fails the divergence test.
Oh, because in the alternate series, you have the three tests where it has to be positive.
Yeah, but
decreasing.
the alternating series test is telling you that if those three things are satisfied, then you get convergence, but the divergence test is telling you that if something doesn't happen, then you guarantee divergence.
Oh, it's not guaranteed.
And so, in other words, series minus 1 to the n times n, right? The limit as n goes to infinity of minus 1 to the n times n doesn't even exist. So it certainly doesn't go to 0, right? Point is that it's not 0, and the only chance you have of something, of the series having a chance is if it goes to 0.
If we wanted to, could we plug in x into our condition? That we got x plus 3 is less than 5? Instead of plugging into the series again?
No.
Can you do that, or?
No.
Okay.
No, because then, I mean, are you saying that then it would fail all the time, right? But we've seen cases where the endpoints are actually
Oh, you're right.
work, right? So that would work. Okay. So, okay, so this would be open interval. In other words, both our endpoints are out, so the IOC is just going to be -8 to 2. That's your IOC. Instead of IOU, it's IOC. Interval of convergence. Yeah. If someone asks you and they say, do you want an IOU? You say, no, I'll give you an IOC, even better, I'll give you an interval of convergence. Did you know that this series converges on -8 to 2? Tell people that, yeah.
Could you explain the open and close again? Kind of the open and close intervals.
Yeah, so the theorem tells us that we always get absolute convergence on the open interval. But the theorem tells us that those endpoints of that open interval, you could get convergence there. But you might get divergence, so you have to check each individually. So we're just taking those individual numbers, -8 and 2, plugging them back in for the variable in the original power series, and then determining by our knowledge of series whether those converge or diverge. Yeah.
When you plugged in -8 and you left the -1 n to the n, what happened to the n on the bottom? So
Well, there was a cancellation.
how does it happen?
Basic algebra.
I'm not
So-
seeing it right now.
So you know that AB to the n is the same as A to the n times B to the n?
Yes.
Okay, so -1 times 5 to the n divided by 5 to the n is -1 to the n times 5 to the n divided by 5 to the n, which is -1 to the n. Right? Okay? So just algebra.
All right.
Okay, let's do one more, and then we'll do some integration and differentiation. Okay, so let's see. Okay, number 33, the sum from n equal 1 to infinity of x to the n divided by 2 times 4 times 6 times 8 times dot 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 times 2n. Okay? And where is it centered? At 0. So it's centered at 0. We can run a ratio test, force it to be less than 1 to get a condition on x. Okay? Let's rewrite this a little bit better. There's a slicker way to write this. Let's do that. Let's see. I mean, isn't this, you agree, isn't this 1 times 2 times 2 times 2 times 2 times 3? Or to be consistent with the notation, it's 2 times 1 times 2 times 2 times 2 times 3 times 2 times 4, right? Times dot dot dot, finally you've got 2 times n. So if I take the 2's here and just make that a 2 to the n, then the 1, 2, 3, 4 n part, in other words, if I take them like this, so if I just look at the 1, 2, 3, 4 dot 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 n, that's an n factorial. So don't I have x to the n over 2 to the nth power times n factorial? Yeah. So we can do a ratio test. So the limit as n goes to infinity, absolute value of x to the n plus 1 over 2 to the n plus 1, n plus 1 factorial, 2 to the n, n factorial, x to the n. Force this to be less than 1. Cancellation all over the place, so cancellation here, cancellation here, cancellation here. So just the n plus 1. So I'm getting, if and only if the absolute value of x is, let's see, if and only if the limit as n goes to infinity, the absolute value of x times, this is just going to be just divided by 2 times n plus 1, yeah? So what's going to happen? We're forcing that to be less than 1, so we're forcing the absolute value of x times the limit as n goes to infinity of 1 over 2 times n plus 1 to be less than 1. Well, do we even need to force? What's going to happen here? 0. So this is true if and only if the absolute value of x times 0 is less than 1, but that's just true. This is just true. So that means there's no condition on x, it works for any x. So we're in case, we're in the case, yeah, where it works for every x, case 2. It works for all x's. So the radius is infinity here, and the interval of convergence is the entire real line. That's for IOC. Okay? Alright, so that covers the interval of convergence questions. I'm going to do some integration and differentiation. Let's do some other. Let's look at this function. Let's look at the function g of x as 1 over x minus 1 squared. Let's try that. G of x is x minus 1 squared, I think I want 1 minus x squared. Maybe I want x minus 1 squared. Yeah, let's do 1 minus x squared. Let's try that. What's the antiderivative of g? Antiderivative of g, this is 1 minus x to the negative 2 power. What's the antiderivative of that? Can you anti-differentiate that?
No.
Is it negative 1 minus x to the negative first?
Close. What about the chain rule compensation?
Oh, there's an extra minus of plus.
Yes. So you're going to use the power rule. So you're going to do 1 minus x to the minus 1 divided by negative 1. But when you differentiate forward, there's an extra negative 1 here from the derivative of this inner. So you have to compensate by putting another negative 1. So it's actually just 1 over 1 minus x. So the antiderivative of g is just 1 over 1 minus x. What do you know about that as a, can you put that in as a geometric series? What's its geometric series form? Whenever you see that 1 over 1 minus r, what are you thinking? Series.
That's when it converges.
Series. Series. What is what is 1 over 1 minus r? 10.2.
Yeah, I forgot.
It's series r to the n, right? So this is series. This is series x to the n. All right. Now, if the integral of g is a series, what's g as a series? Let's say that again. If the integral of g, the antiderivative of g is a series, what's g as a series? The derivative of the series. Yeah, if the antiderivative of g is a series, then the derivative of that series is g. So g, in other words, is the derivative of this series. Now we had a nice theorem that says if you want to differentiate a series, you can take the series of the derivatives. You can differentiate them term by term. So in other words, this is going to be the series from n equal 1 to infinity, because the first one is a constant, the derivative constant is 0, it falls out, and it's going to be n x to the n minus 1. And so this series now represents this function when the absolute value of x is less than 1, because that is where this geometric series is converging. So this trick allows you, in other words, if you see an a over 1 minus r form, you can put that into your series a r to the n. Now if I gave you a function like this, its antiderivative can be written in this form. You could then expand the antiderivative as a power series, and then you could differentiate back to recover the original function. Or as we did, what did we do in last class? We were looking at like arc tangent. So last class we said the derivative of arctangent was a 1 over 1 plus x squared, which has that form 1 over 1 minus a minus x squared. We then expanded this to be a series. We expanded this to be a series. And then we anti-differentiated the series to recover arctan x. So arctan x turned out to be the series from n equals 0 to infinity of minus 1 to the n x to the 2n plus 1 over 2n plus 1. So this is kind of a trick to bypass what I'm going to show you right now, because it's quarter of, and we're going to spend the next 45 minutes with Taylor, is going to bypass the more complicated or theorem that comes in with Taylor series. So I'm going to show you a formula for Taylor series. These can be done really quick because you're making use of that geometric series form. But in general, you won't be able to do this. You can only do this if your function's derivative or antiderivative is in this form. That's not always going to be the case, right? So let's look at Taylor now, okay? So we're going to do the following, okay? So I'm going to assume that my function, let's assume that our functions, like our nice functions like sine x and cosine x and e to the x, and these functions that you've been working with, let's assume that you can write them as a power series. So let's assume that our function is a sum from n equals 0 to infinity of Cn times x minus a to the n. What would these Cn's have to be? So the question is, what are the Cn's? So I'm going to show you how we figure that out. So, in other words, f of x, let's write it out. F of x is going to be C0 plus C1 x minus a plus C2 x minus a squared plus C3 x minus a cubed, C4 x minus a to the fourth, plus dot 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 dot. You get the idea. Now let's differentiate this. Let's differentiate this equation. So f prime of x, now remember the theorem says that you can differentiate a series, you can differentiate a power series term by term. So this is going to be 0. What's the derivative of c1 x minus a?
C1.
C1. What's the derivative of c2 x minus a squared?
2c2 x minus a.
2c2 x minus a, and then etc. So 3c3 x minus a squared plus 4c4 x minus a cubed plus dot 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 dot. What's the second derivative? What's the derivative of c1? No, 0. Differential with respect to x. What's the derivative of 2c2 x minus a?
2C2.
2C2, the constant, right? 2C2. And here we're gonna get a 2 times a 3C3 x minus a, right? And here we're gonna get a 3 times a 4C4 x minus a squared and dot dot dot. Okay, let's take the third derivative. What's the third derivative? 0, right? 2 times 3C3 plus 2 times 3 times 4C4 x minus a plus dot dot dot. Let's do it one more time. What's the fourth derivative? It's just going to be 0 plus 2 times 3 times 4 times C4, right? Plus dot dot dot. Okay. Let's kind of see the pattern that's happening. Let's now toss in A for X. In other words, let's create another pattern. What is f of A? What's f of A? Just plug A in for X everywhere, and what about this? 0. Okay, what's the first derivative of A? I don't understand. Why can't you just plug in? Why can't you just plug in A on the right hand side and tell me what you end up with? C1. Yeah, all of these will be 0, but you still have the C1. Okay.
We're talking about that.
Now, what's the second derivative of A?
2C2.
2C2. What's the third derivative of A?
6C3.
Okay, instead of saying 6, I'm going to say 3 factorial C3. What's the fourth derivative of A?
4 factorial C4.
4 factorial C4. You see a pattern.
Yeah.
Okay, so what do you think the nth derivative of A is?